Laurence has very kindly agreed to give me a few minutes at the beginning of this talk to provide a little bit of a roadmap for what you're going to hear over the next 2 days. So there will be 8 talks, 7 talks by collaboration members, and then we've invited one external person to tell us a little bit about the current landscape of the cosmological surveys and the challenges. So the collaboration has been in existence for about 4 years. Our goals are, as I'll describe in a little bit more detail, are to develop a principled understanding and computational model for star formation, galaxy formation, black hole accretion, and feedback, such that they can be put into cosmological simulations, which are then used to compare against cosmological observations, the large-scale surveys which are coming out, in order to infer both properties of how galaxies form, but also cosmological parameters and the initial conditions of the universe, so where we came from. So in order to do this, we have assembled a group of people. So this is the list of PIs from about a dozen different institutions, and they are experts in a wide variety of fields, from star formation to black holes, to statistical inference, to machine learning, to cosmology. And one of the goals of the collaboration is to encourage crosstalk across these different groups. They speak very different languages. They often publish in different journals. So one of the things we've tried very hard is to develop a coherent and collaborative environment. And so what you'll hear, though, is actually mostly talks not from these PIs, but from collaboration members about their work, about the work of the group that they are involved with, and how that connects to the full collaboration goal. So the collaboration, of course, is nothing without its people, and I just want to encourage you to look at this list. Many people on this list, not all of them, are here today, and please do engage them in conversations and ask hard questions to try and to encourage us to think about new ways to develop new connections. So that's who we are. I want to take a little bit of time and give you a quick roadmap to what the motivation is, and what we are and how we are planning to go about that, what our goals are. So one of the motivations is this cosmological inference. It's learning about dark energy, about the fundamental physics, which drives the expansion of the universe. And of course, one of the motivations is that all of these surveys are now, or many of these surveys are now actually taking data. And that's great. There's going to be this wave. In fact, there already is a wave of data which is coming, and we need to interpret it and infer it in a principled way. But in order to do that, we need to develop the methods that make use of all of that data, from large scales to small scales, from luminous red galaxies to secondary anisotropies. We need to squeeze out as much information from that data as possible. The second motivation is to try and understand our origin. Where do we come from? This is important for a number of reasons, one of which is that the initial perturbations which gave rise to us, to large-scale structure in the universe, probably has information about what's happened in the very few first, the seconds of the universe, about things like the inflaton potential, about the physics which gave rise to that structure. So particularly things like non-Gaussianity. We want to try and measure these initial conditions in order to make constraints on that. But also, we want to touch base with the universe in which we exist. And you'll hear about simulations of nearby objects in a cosmological framework. And then the final motivation, as I said, is to really understand galaxy formation. This is a very complicated system, but fundamentally this is key to everything that we observe. And so we need to understand that if we're going to understand, if we're going to use all of that data in order to make the constraints. And it's an interesting topic all of its own. Many of us are motivated primarily by an understanding of galaxy formation. So how are we going to go about tackling those three problems? So here is our overall strategy. And what I'll do is I'll emphasize it. I'm going to give you a big picture. And then the talks that you hear, and I'll try and give you a roadmap for those various talks where they fit in, will hopefully answer more of your questions. So I'm going to provide just the large scale. So this is what we would like to infer is as I said before, not just the cosmological parameters, but also the understanding of galaxies and these initial conditions. So how do we go about doing that from observations? Well, ideally, we would have an inverse problem that we could solve. We would take the observations, and from that, we would directly measure all of these things. But of course, we all know that this inverse problem is not the right way to go about doing that. It's not tractable. There is no way to do this principally, in a principled way. Instead, we're going to use the standard idea of Bayesian inference in order to do this. So in particular, we're going to sample from this posterior of all of these different uncertainties, put it through a forward model, predict some set of observations, compare those observations to the observed system, so whether that's the distribution of galaxies or the cosmic microwave background or other sorts of kinds of observations that we might make, and then measure the likelihood, the similarity between these two. And that is its own challenge, but I'll get to that in a second, and then repeat this process in a standard Bayesian loop and develop a posterior distribution for the unknowns on the left. Of course, that's a great, simple problem, and for a few parameters, I think we've all done something like this, but we're not talking about a few parameters in this case. We're talking about millions or billions of parameters, and the forward model is maybe a 10 million CPU calculation to go from the initial conditions to predictions of the galaxy distribution. So this is hard, and it requires new approaches on both of these fronts. So here is our approach in a nutshell. This is a lot of text. I'm going to go through it. But basically, there are three key things that we are going to do. One is develop new models for galaxy formation. So in particular, understand how star formation and black holes regulate galaxies and the gas around them. Second, we're going to accelerate those expensive simulations by factors of millions, or hopefully even more, so that we can speed up that forward model and actually be able to do some sort of inference loop. And then finally, we are going to develop new ways, or have been developing new ways to handle the likelihood, because this likelihood is not easy to write down. It's not a simple Gaussian distribution. So I'm going to go through each of those three things, briefly talk about the previous sort of standard approach, and then contrast it with what we're trying to do here in this collaboration. So the standard approach in galaxy formation simulations, and as I go through all of the previous approaches, I don't mean to denigrate them. I think they had made fabulous progress. I just think that we can do better. So the standard way to do cosmological simulations in the past large-scale simulations is to take a single best guess from these parameters, tune some sort of subgrid model based on the data, and then do a single or maybe a small number of forward models and generate simulated data. Obviously, this is challenging to do inference because we only have a few forward samples, and we've double dip. We used our observed data to constrain our model. So we can't do this inference. So our approach is to use subgrid simulations, highly refined simulations of individual areas of star formation, black hole accretion, and feedback, and use those to inform the forward models so that we're not using the data to constrain the model. And just to look forward, you're going to see a talk by Sophie Kudmani about our efforts to do this in black holes, and also from Chang-Gu Kim to talk about how we're approaching this in terms of star formation and feedback. And then finally, these need to be taken and put into a cosmological simulation on large scales. And Uli Steinwandel is going to talk about efforts in that. So that's the cosmological simulation. That's the first step. The second step is this forward modeling step, right? So the standard approach has been on large scales to do some sort of in-body simulation or maybe some sort of quasi-linear approximation, use a simple bias or more complicated, a halo occupation distribution to populate the dark matter simulations with galaxies, and then to do an inference here. And these steps are fast, so they can be done easily. But what we would like to do is use these forward models to not do one simulation, as I described before, but to do an ensemble of simulations. So, sample from this distribution of simulations, of initial conditions, of astrophysical models, and then forward model. And this has been, the CAMEL simulations, CAMEL's collaboration, which is the members, the eyes of that are also members of our collaboration, have pushed far forward, and you'll hear an update on that from the Training Set Generation group. Shai Ganil will describe that. So exciting new approach efforts in that regard. So then, we'll take those ensemble of simulations and train them for machine learning models. But that's not enough, because we want to make this comparison in the observed space, the observational space, not in some sort of theoretical space. We want to compare directly to data. And so we need to develop these synthetic observations. And you'll hear a talk given jointly by Lara Somovico and Shivam Pandey, talking about our efforts in that regard for both galaxies and for the cosmic microwave background. And then, and I'm eating into Laurence's time here, so I'll be quick. One key aspect of this, of course, is that this is no good unless we have these rapid accelerated forward models. So Laurence will be talking about efforts in that area. Okay, so the final thing, the final area is the inference itself. So again, this is sort of the previous approach, is to do this modeling, compute some sort of summary statistic like the two-point power, or the two-point correlation or the power spectrum of galaxies, and then do the comparison in this small summary statistic space, and just assume that the likelihood is Gaussian. What we'd like to do instead is use the forward model that I just described and put us into this observed space, compare against observations, either using an implicit or explicit likelihood, and put this into the inference loop. There'll be a talk by Matthew Ho about using simulation-based inference, or as we like to call it, implicit likelihood inference, so that we can infer what the likelihood looks like. We don't have to assume it a priori. And then Stuart McAlpine will talk about a parallel effort, or actually they're growing together, of doing this with an explicit likelihood, but applying it to infer the actual initial conditions. So the millions or billions of parameters that describe the distribution of galaxies on the large scale. That's the roadmap. That's what you're going to hear about in more detail over the next 2 days. And I just want to put it all together, just so the cosmological simulation, the models, the inference, the training, and all put together. Of course, so as I emphasized, this is no good. If we can't rapidly, if we can't do this step in particular, this machine learning accelerated forward models. So to tell us more about that, I'm going to bring up for the rest of the time Laurence, who will tell us about the collaboration efforts in that regard. And at the end, we'll take questions jointly. Go ahead.
All right. Thank you so much, Greg. So I'll try not to go through all of the bingo words like right now, so that you still have some fun for the rest of you. If you don't have a bingo card, you should definitely get a bingo card. It's like one of the highlights of the conference. Okay. All right. So this should work. No, it doesn't work. Okay, all right. So I'm going to be telling you more about some of the work that the collaboration has been doing on accelerating forward models and robustness. So a lot of this is not my work. So if I say anything wrong, just wave a flag and correct me, okay? Why does it echo so much? Is it this? I shouldn't be talking like, okay. It's not my ear that's, wow, this is not good. Ooh. Okay. All right, so I'm going to, why is this making this sound?
This was working, it will work again. Yeah,
it's just ringing in my head.
Just push that.
Okay. All right. Okay. Good. All right, I'll bring this up again. So I feel like I'm in a fish tank. I'm sorry, I think I'm getting an ear infection right now, so I really don't feel good at all. It's extremely painful. So I'm gonna try to get the words together. And it's going to be just fine. Okay, so this is the plot that Greg showed, like a whole bunch. And so I'm going to be talking about this forward model here, which is really important because that's how it maps our initial conditions and like specific choice of cosmological parameters to a set of observations. So in our case, great. So all right, so let's go like that. So in our case, that forward model comes from theory and simulations. And it's really, really important because that's what allows us to connect like the parameters that we care about to our observations. And so in the case of cosmology, in principle, we know what this is. Because if I give you a set of initial conditions, what drives the evolution is gravity and hydrodynamics. So here I'm showing a simulation of this from the hydro, I really like much better to do my laptop because this is not working. My fingers are not working well right now. Okay, so that's an example from illustrative TNG, but if we get this, that's not all because if we want to make the link to observations, we also need to run dust radiative transfer simulation, and then also a light radiative transfer simulation. And then if we actually want to connect to observation, we also need to add all the observational effects like convolution with the PSF and observation noise and all different kinds of observational effects. So all right, so that's a tall order. So can we actually do this? So if we knew what the subgrid physics model is for the actual universe, and we wanted to run a simulation like a hydro simulation on like a small box of say 25 megaparsecs cube, and we wanted to resolve halos down to say 10 to the 7 solar masses, because I care about the physics of dark matter, then it would take about 150 million CPU hours to do that. And then we'd still have to run the radiative transfer simulation. So right now, with Sphinx, that I think is still the best code for doing that, it would take about 63 million CPU hours to reach a redshift of like 4.5-ish. And so that's pretty expensive. But then that's not all, because we don't want that on a small box. We actually want to simulate like a big box to match to the current footprint of like current generation surveys. So we would actually want to simulate this over volumes of like 10 gigaparsecs cubed. And so that means that we would need to multiply this simulation time for one simulation by a factor of 500 cubed. And so that's just for one simulation. And so we would need many simulations because we want to understand how how our parameters of interest are affecting observations in order to constrain them and understand our uncertainties on recovered parameters. So we need to run many of those simulations. So clearly, that is not going to happen. So what do we do? What can we do? So typically, the way that we go about this problem is that we break it down in multiple steps, and then we can use various levels of approximations for all those different steps. So typically, this goes like we're going to try to start by a gravity-only simulator solver that's going to allow us to get the distribution of dark matter. And then we're going to impaint galaxies onto that dark matter field with something, and then that's going to allow us to get a galaxy catalog. Then from that, we're going to measure summary statistics, and then we're going to compare that to summary statistics measured from observations using typically a Gaussian likelihood. So the kind of approximations we might do for those various steps, well, for the gravity solver, we might use something like perturbation theory, because that's very fast, or something like a particle mesh solver. For the galaxy model that we're going to put on top of that, well, there's a whole array of things that we can use, from like much more like physical and much more expensive models to much simpler models like HOD models. And so that's like kind of menu of choices we can make here. And then from that, we can get a galaxy catalog. And in terms of summary statistics, we might want to do something like measure the power spectrum, or like the bispectrum, or other cross correlations. And then the likelihood is typically assumed to be Gaussian with the covariance that's evaluated around some like fiducial cosmology. So that's the traditional way of doing things. So much in a much more like pictorial way, linking to math talk. So we start from some initial conditions, and then we pick our dark matter only solver to get some distribution, Lickat distribution of dark matter. And then I had the pointer, yes. Okay, pointer. And then we're going to do some like we're going to figure out where the halos are with some like halo finder. Then we input galaxies on top of that. Then we get the light cone, we put that on the light cone. We add our observational effects, we get our summaries, and then we can compare with summaries measured on the real universe. And so what I'm going to be talking about in this talk is how to replace this part with and that goes on next year, and then this part with an emulator, and then Matt, and not the next talk, but the talk after, is going to talk about how we can put all of that together and replace this Gaussian likelihood by some simulation-based likelihood that you can learn without having to specify exactly what the analytical form is. All right. So let's start by the first emulator, which is emulating dark matter-only simulations. So the game plan here is that what we want to do is basically we want to replace expensive n-body simulations by some form of machine learning method that's going to take in like the initial conditions, and then is going to give us the final distribution of just the dark matter. So replace the need for solving like all gravity. So the first simplest thing we could think of doing is say, I'm just going to put a big neural network there and just solve all my problems for me, and I'm going to be done. So a lot of people have done that, and it's actually like a valid strategy to take. So typically what works better is that you would just use some like analytical approximation to that, like the Laurence approximation or some perturbation theory approximation, and then you're going to use a neural network, like a big neural network like a VNet or a UNet, to predict corrections on top of that. So there's a lot of work in the collaboration that's focused on doing this in various flavors, and I'm not going to have time to talk about that, but all those people have worked really hard on this, and it's going to be covered in the Borg's talk, in Stuart's talk. So he's going to talk more about this. But then, of course, those emulators, they make mistakes. But the thing that's really cool is that you can actually include a correction term in your evolution equations in the potential, and then solve for that and actually correct for those trajectories. So that's also something that's very cool that Declan has done. That's going to be covered in Stuart's talk. So stay tuned for that. All right. So the thing with those things is that because they require training a very big neural network, you're going to still need a very large training set. And you're going to be dependent on like what's the coverage of your training set compared to the span of cosmological parameters that you want to infer. And another thing is that you're going to be constrained into predicting like training your network to predict a specific redshift. So you're not going to have like the whole time evolution of your universe once you've trained a network like that, which is something that you might be interested in getting. So in parallel to that, actually, over the recent years, with like differentiable packages, there's people have started writing n-body codes in a differentiable way, in a way that can be run on GPUs. So things like PM simulations have started to be written in a way that you can run it on a GPU, and that makes it much faster. So like PM codes can take like as small as like 3 seconds for Camel's like volume. So that is a really big game changer. And there's no machine learning here. It's just being smarter about the way you write your code and making it faster. So if there was a way to leverage this, it would be like very good. So the way that those PM simulations work is that they write down the evolution equation. So that's just F equals ma for a galaxy where you have the force that acts on the velocity. And so that's just for this, it's a gravity-only thing. And so the force in an like pure n-body simulation, you have to calculate the force between every pair of particles. So it scales really poorly with the number of particles you have. But one approximation you can make is that you can say, well, I have all those particles. I'm going to project them down onto a grid to have a potential, and then use the gradient of the potential to get the force. So then I don't have to calculate the force between every pair of particles. So it scales much better with the number of particles. So basically, you can say, I'm going to do this, get my force as the gradient of my potential that I calculate like that. The catch here is that because you have to project your particles down onto a grid, that grid is not infinite like resolution, and so that introduces some coarse graining into your forces. So you lose some resolution. So what happens is that the resolution of your final simulations is going to be much poorer on small scales compared to the full n-body simulation. So basically, on small scale, you get some error that accumulates as you're integrating your evolution equation. But it's still pretty powerful because it's extremely fast. So can we do something with this? So the problem with like these poor resolution, like the PM-only simulation, is that they are not precise enough to run a halo finder on them to be able to just find the right halos and then keep on going with your methodology. So we would need to basically have, it would be really great to have some kind of machine learning model that allows you to go from this like PM simulation and then go straight to finding what the halos are, basically replacing the step of needing to run the really high resolution simulation, running the halo finder, and going straight to finding what are the halos that correspond to this simulation. So the first round of doing this is with Pine Tree. So I'm not going to talk about this one because I think that's going to get covered in the Borg talk. But I'm going to talk about sort of the next generation, which is Charm, for doing this. So basically what the strategy is here is to take a large volume, low resolution PM simulation. And like by low resolution, I mean like in one halo, you'd get maybe like 3-4 dark matter particles. So that would really not be enough to run like a halo finder. And then you take those simulations, you embed, so for, you basically embed a small volume around the place, the voxel where you want to predict what's the number of halo and their properties going to be. You embed them in some latent space, and then you do, God, the words. Yes. Okay, so you output something, and then you feed it to itself to get the next one. I'm just playing. It's, there's a word. Yes, exactly. Bingo. Okay, so you physically predict the number of halos, and then from that you're going to autoregressively predict what's their mass and what's their properties, like their position, you know, but like their mass, their velocities, and also their concentration for every voxel that you have. And then you can scan through your whole voxels, and then you get the whole like catalog of your halos with the properties that you care about. And then you can move on and do your HOD modeling, and then you're done, which is super great because then you had to run just a really cheap n-body simulation that's really low resolution, but then you get the same benefits as if you had run a really expensive n-body simulation at higher resolution plus like Rockstar on it. So it's great. But so there's some limit, however, into like how high resolution you can go. So the next generation of that, comparison with stuff. So you can actually like take these catalogs and then like do predictions for observables. So this top plot is a comparison of that. So in blue is what you would get, the colors are different cosmologies. The markers are predictions from n-body only, and the lines are what you get with Charm. So everything agrees like really well. So it works super well, even like in redshift space. And then you can take those predictions and then say, okay, what if I wanted to do inference with those? So you train some ILI model, like what Matt is going to talk about. And then you test on something that's been run with a full n-body simulation, and you see that you're in distribution and it's not biased, and it's great. So that means that it's very good, and it's 1,000 times faster than what you would get if you had to run the full n-body simulation. So that's a great speed gain. So next generation of this allows you to go to even smaller scales. So with Gotham, which is the next generation of this, basically what you do is that you do the same thing, except the embedding is done with a transformer now. And then the strategy here is that instead of training this series of normalizing flows that predict things autoregressively, you're going to treat this problem as a translation problem between your point cloud of like galaxy, of halos and their properties, and your like density map, basically. And you're going to teach your network to translate between those two. So you give it this thing that you embed in some embedding, and then you translate into the list of halos. So that's basically and their property, which is the strategy that you adopt here. And then doing that is actually a lot more powerful, because like data transformers are great. So, and then you can go down to like much smaller scales, basically up to like k of 1. So that's super promising. One thing is that we would like to go to even smaller scales, ideally. And but one thing that's limiting is that we still start from this low resolution n-body like approximate field. So there's some information that could have been erased already there. And so if we could start from some input that's even higher resolution, maybe we could go down to like much smaller scales, even with something like this. So is there a way that we can generate very fast pure n-body simulations that could be used as an input to something like that? So basically, is there a way we could basically correct our PM equations in a way that it corrects for the small scale? So I said before that this is what we do in a PM simulation. We take our particles, we project down in a potential on a grid, and that's where the error comes from, because I have coarse grained. So basically, the thing that's happening is I'm missing the closure for this cross-graining operation. There's something that comes from like scales that are smaller than my grid that's going to affect the evolution on scales that are close to the coarse graining scale. So what I could do is I can put some neural network inside my equation and learn what this closure is from a high resolution simulation like this. So this is what I showed before, PM kind of blurry, n-body not blurry. And then if you do that with a term like this, then you can recover something that's extremely close to your n-body simulation with the same speed as you had during just a PM simulation, which is great. So my student, Nicola, he's been working really hard over the past year to make this run on parallelized across GPU so that he can run really large volumes extremely fast. So basically, this is an example of what this is. So you can zoom in on like a small region, and you can see that the distribution is extremely close to like the n-body even on very, very small scales. And so you can go on and compare summary statistics at different redshift, because now you know the equation, right? You have one neural network but it corrects the evolution equation. So you can still integrate your ODE up to like with whatever like time steps you want. So you can get all the redshifts, and they're all self-consistent because there's one equation that you're evolving. It's just that there's a component of the equation that's a neural network. And so that gives it much more like chances of being robust to things like out of distribution, because you've learned the actual evolution equation. And so it's a lot more interpretable as well. So you can go and run output the power spectrum at whatever redshift you want, and you can see that you get up to like k of 30, you're accurate with more than like 95%, basically. In the power spectrum and the cross spectrum as well is like really bang on between n-body and the PM++ simulation. So we can do things like, whoa, what happened? Okay, sorry. So you can calculate you can run Rockstar on your simulation and get your halo mass function, and it's very accurate. It would probably be accurate enough to find a merger tree, and maybe that would be another approach to try to run SAM on these very fast n-body simulations. So that would be something cool that would be worth exploring. And then we can also use the same code to generalize between different sizes. So we can run the same code either at like this Camel's volume or like Quixote volume or Camel SAM volume. These are all different like volumes of simulations. We can do that, and it scales extremely well with like the number of particles and the size of the grid. So it's about 1 second on to run one of those simulations on the volume of like Camel. So it's very similar to just regular PM codes without the correction. So, yep. So all right, next stage is, all right, now we have a way of doing n-body only. I have no 25 minutes. That's not optimal. Okay, all right, so let's zoom through this very quickly. So we need to learn, well, we have dark matter like distributions. We need to in-paint stuff that we can see on top of that, because we don't observe dark matter, we observe galaxies. So one thing that Chris did a couple years ago is that he realized that you can use a series of normalizing flows to go from just the cosmological parameters to halo mass function and like properties, but this still doesn't allow you to do like the field level inference. So Niall and Ben, they've been working on this method to do using wavelet net moment matching words. Wow. Ben, can you help me, please? Yes, that. Thank you. So basically, the idea is like when you can do macrocanonical gradient descent to generate samples that are going to be of maximum entropy, starting just from your power spectrum, to have field levels that like sample well. But this is really slow because you need to basically do the gradient descent thing. Whereas here, they replace that gradient descent by just like a neural network that you train once, and then you can generate as many as you want. And instead of matching the power spectrum, they use wavelet moments. And so the thing that's very cool is that you can actually, it's equivalent basically to two things. So that's really a super powerful thing that could be used for generating field level emulation of fields that you can observe. Other approaches that we're exploring right now is to use transformers. So basically, we had gotten before that went from like low resolution PM simulations and produced halo mass functions that were as the same quality as Quixote. So now we could use those n-body simulations and PM pop plus simulation and then map straight to galaxy properties using the same transformer. So basically translate between dark matter to galaxies. And this seems super promising, but it's also a work in progress, so stay tuned. And then another thing that we can do is to use diffusion. So with my student Antoine, we showed that you can train a diffusion model to basically condition on dark matter density maps and predict the number count of galaxies in every voxel that you have in your simulation. And then you can show that you're in distribution, and it's great. And then you can use that to do inferences to show that you're not biasing yourself in a way that you would be blind to. And then with Amanda, what we're doing right now is we're going to use this output of like how many galaxies you're going to have in every voxel to initialize a point cloud. And then we can run diffusion on that point cloud to predict their properties. And so that's also work in progress, so stay tuned for that as well. So we have a lot of different possible way forwards to model galaxies and their properties that are going to be developed over the next year and coming years. Okay, so I'm going to skip over that and then talk about robustness. Okay, so I talked a lot about how do we do emulation and how we try to map what a simulator does with like a fitting function, basically. And Matt is going to talk a lot about how you do inference in cases where your like parameter space is high-ish dimensional, but your data space is also really high dimensional. And so I hope that like in the coming today and tomorrow, you're going to get convinced that like with machine learning, we're really going to start to be able to do inference problems in high dimension, starting from high dimensional spaces in a way that was just completely intractable previously. So in that sense, we need to be able to convince ourselves that like we're doing the right thing. So we need to answer like two separate questions. So the first question is like, if I give you a pipeline that produces posterior samples, how do I know that those posterior samples are accurate? Like, how do I know that I'm actually getting samples from the real posterior distribution, not some other distribution that kind of looks-ish like the posterior? And the second question is like, if I replace some component of that pipeline by a machine learning model, how do I know that that machine learning model is doing what I think it's doing, right? Like, how do I know that my emulator that I've replaced is actually representing well the function that I asked it to replace? So for answer to the first question is TARP, and answer to the second question is PQ mass. So I'm going to talk about both these things. If I have time, I have no, this is to the hour, right? So I have like 5 minutes technically. Okay, that's fine. All right. Oh, so same target. Okay, right. So typically, so let's start by the first question. So the question of like accuracy. If I give you a method that gives you posterior sample, how do you know if that method is, if those posterior samples are from the actual posterior or some like other distribution? How do you measure that? So typically that's done with something that's called the coverage test. So a coverage test is like, let's say that I repeat an experiment multiple times, and I get like confidence like intervals. It's the fraction of time that the ground truth is going to fall within an interval. So let's say I look at the 68% confidence interval, so it's going to be like here in one dimension, and my ground truth like falls inside my like 1 sigma interval here. So what I would like for my posterior to be accurate is the ground truth to fall inside there 68% of the time. So typically you would like the coverage of an interval to be equal to the amount of posterior mass that you have in that interval. So typically, that's what it says. And you would like that to be true for every possible like interval. And so if you plot the mass in the interval versus its coverage, you'd like to have a very beautiful diagonal line like this. And if it's not accurate, it's not going to be a diagonal line, because some of your regions of your posterior are going to have too much mass or too little mass. So typically traditionally this was assessed with something called the highest density regions, which is basically the smallest region that has that mass. And so here's like the peak of the thing. But there's no reason why I should have chosen this. I could have said, okay, like the 58% like the 50% like interval, it could have been like from minus infinity to the peak here in the case, because it's going to have 50% of the mass, right? And I'd like still the ground truth to be in there 50% of the time. Okay, but this is the way that this is typically assessed. There's a lot of problems with doing it like that. First is that in really high dimensional spaces, like even, and like I don't even mean like in 10,000 dimensions, like even like 10 or like 20 dimensions, if I give you a bunch of samples, like how do I know where is the highest density region? It's not super easy to estimate. So you could do something like KD to do some density estimation, but that's not going to be very accurate. So you might bias yourself even just from the density estimation itself. So having to go through the density is really not ideal in a case like this. And then the second thing is that it's not a sufficient condition for calibration. So what I mean, like I can give you a really example for this. So one example that's really easy to see is if my posterior is symmetric, like what I've written here. If I get a case like this, where my ground truth is always to the right of my posterior, then I'm going to pass completely a coverage test. But this is not accurate, because everywhere where I've given some density here, I know for a fact that the ground truth is never going to be in there. So this is not an accurate posterior. Okay, so this is a sufficient condition for like calibration, but it's not a necessary condition. Sorry, the other way around. It's a necessary condition, but it's not sufficient. So it means I could pass the test and still be biased, and I wouldn't know. So we'd like to have a test that's a sufficient and necessary condition for calibration. So with my postdoc, Pablo, and also Adam Coogan, so what we've done is we've basically designed a new coverage test where we look at different density regions inside the posterior that are randomly generated in a way that if we average over a lot of those regions with a lot of different posteriors, and we pass a coverage test, then we're guaranteed that we're going to be calibrated. So we've proven a theorem that's a necessary and sufficient condition for calibration. So it means that if we pass the test, we're guaranteed to be calibrated. So that's super great. And the second thing is that it scales really well to high dimensional spaces because it doesn't rely on having access to the density. It only relies on being able to calculate distances between points in parameter space. So if you can, and it could be whatever metric distance you want. It could be the L2 distance, which is really easy to calculate in like 2 million dimensional spaces. And then you can calculate that metric distance, that distance between all your points, and then you get your coverage, and you're done. So that's great. So the way that it does in practice, if you're calibrated, you get the diagonal plot. If you're overconfident, you don't get diagonal. If you're underconfident, you don't get diagonal. But then the important thing is in the case where it is biased, so you would not like to pass the coverage test, the case where you would only look at the highest density region, you would fool yourself into thinking you're calibrated, but the TURP test is going to detect that it's not, actually. So you're going to be able to go and find where are those inaccuracies coming from. Okay, so that's for TURP. So that allows us basically to know when we have a posterior estimator, is it accurate or not? If we get the diagonal line, then we're guaranteed to be calibrated, and if we don't, then it's inaccurate, and so we need to work harder to find out where these inaccuracies come from. Okay, so that's for question number one. Question number two was if I have like an inference pipeline and there's some component that's been replaced by a machine learning modules, how do I know that that is doing what I think it's doing? Okay, so and that's something that was just published this spring in iClear. So basically, it's sort of the same strategy of trying to tessellating the space in different regions. And so the way to see how this comes about is, like I said, I have a region and I have two sets of samples. They could be like one set of samples is from my emulator and one set of sample is from my true simulator. So if they come from the same underlying distribution, like in like pixel space, for example, then the chances that I have some number of samples out of like n samples in a region is going to be given by a binomial distribution. And if they come from the same underlying distribution, it's going to be the same binomial distribution for my red and my blue samples. So that's for a single region, but I can also completely tessellate my space, and then it's going to be given by a multinomial distribution over all like the different regions in my space. So what I can do is I can define like a chi-square statistics that tells me what is the chance that I've randomly drawn those two sets of samples from the same underlying distribution. This is basically my null hypothesis, that they've been drawn from the same underlying distribution. What are the chances that I'm going to get disrealizations of sample? And so I define this like statistics, this chi-square statistics, and the thing is that if I retessellate multiple times with multiple different realizations of my sample, that statistics has to be chi-square distributed, basically. And so, yeah, so this is what's written here. Given any sampling distribution or any generative model, if two sets of samples are from the same distribution, then this statistics is going to follow a chi-square distribution. So it's true for synthetic distributions like this one here that's multimodal, but it's kind of a bunch of Gaussians in like 100 dimensions. But it's also true for natural images like MNIST digits, like this, because they're just samples in high-dimensional space. So that's really interesting for like two reasons. So first of all, it works directly in pixel space, so I don't need to embed my data in some latent space that could be blind to some feature of my data that I care about. So like in an adversarial scenario, you'd have to like train a classifier that's going to project your data down in 2 dimensions, but then you could be blind to a lot of things that you might care about, like your noise statistics or things that like when you do science is very important. And then the other thing is that it only it relies on defining a distance, again, between points, so it scales really well to high-dimensional spaces. So I can compare distribution of n-body simulations directly, like, at the field level. So I can compare distributions at the field level. I don't have to compress anything down to, like, power spectra or bispectra or things like that. I can do all my comparisons directly at the field level and know if I'm producing things that are in distribution or not. So I'm going to skip that. So this is really powerful. So things like if I'm training a machine learning model with two completely different architectures, two different types of model, I can track how well I'm doing as a function of training and objectively decide which of the model is better. So this is like comparing if I'm training a VAE or a diffusion model on MNIST data. We can see that like at the end of training, the diffusion models are much better than MNIST because they converge to a value that's closer to the optimal distribution. And we can, so Matt's going to talk about that. You can do field level comparison, and you can also compare, even if there's no emulator, you can also compare, let's say I have different n-body codes. There's no machine learning here, but do they produce simulations that are in distribution with each other? And the answer is no. So that's interesting. So Matt's also going to talk about that. So yeah, and then I've talked about things like at field level and boxes, but it's something that doesn't just rely on like having images. You can apply it to any modality, as long as you can define the metric distance. So you can apply it to tabular data, protein data, time series, spectra, whatever you name it. As long as you can define the metric distance, you can apply it to see if you have things that are in distribution. So I'm really running out of time, right? I should just stop talking. All right, so I think, yeah, so I was going to talk about, I think I should talk about, oh no, there's more slides here. Okay, I should have removed those, okay. So what I wanted to do is just mention this very quickly, because I promised Niall that I was going to mention that, because it's very cool. So like I've talked about, like if I have a posterior, how do I know it's accurate? If I have a generative model, how do I know that it's doing what I think it's doing? So the last thing I'm going to mention is how do we do model comparison? And so that's Niall and Ben's work. And so they came up with, it's basically a ratio estimator that they train to calculate the ratio of the evidence. So a ratio estimator is basically a classifier that you train to predict if samples come from one distribution or the other distribution. So typically, you're going to sample from the joint, and you're going to sample from the product of the marginals, and then you're going to try to classify if it's like from the joint or from the product of the marginals. And you can prove that this will converge to exactly the ratio that you want. So they basically came up with a clever way of defining this loss function so that this classifier converges to the ratio of the evidence. And then you don't need to do any like evidence calculation, any integration. It's great. And then you can do model comparison. It's this way. And if you want to get the evidence actually even more accurate than something like polychord that would do nested sampling, that would be extremely expensive. But here you can get the evidence much more accurately with something like that. And another thing that's like super cool is that if you sample model 0 from something that gives you just a constant, then you basically have access directly to like the evidence itself. And so that gives you a way of doing prior predictive tests. Basically, if you have your data, you can sample from your prior to get like a p-value to know how weird is your data compared to what you're expecting from your prior, and you can do anomaly detection in this way. So that's another cool thing. And I'm just going to stop talking now.